So, the wide body radiation.
X-ray. Oh, that's where you can see. This is very hot plasma. So it shows up different than and if you look with your eye, right?
Right.
That's gonna look more circular. So essentially, both scientists are working on things, and so over the course of the year, you may find that this team really hasn't been doing this team very much, and so you organize a meeting, and then everyone presents what they've been doing for.
Is it different every year, the location? Or the
Well, I've only been on the team for last year and this year. Last year was Tokyo.
Oh, wow.
Pretty cool. Yeah, my first time to Tokyo. And this year's Paris. I'm in Paris a lot, but that's because we have a lot of European collaborators.
Yeah.
In Europe, the European Space Agency has a major center in Belgium and another in Spain. So for many French and Spanish, Belgian, German, you'll go to one of those 2 or 3 places.
Howdy.
You go from a geology party? Come from a geology party?
Yeah.
Nice. Think folks are gonna be late because
There's a physics party downstairs.
Well, seriously,
Yeah, they were.
almost looked like they weren't gonna pull it off.
Oh, no, never had a single doubt. Never had a single doubt.
I was thinking they would come back though and finish it here in LA.
Mhm.
That was my thought.
No, I had lots of doubts.
Especially after Tuesday.
Well, even the way that the game began yesterday.
No. Tuesday I wasn't that worried, I was intentional, right? I have 3 starting pitchers. Give folks another 4 minutes. If you want to go grab more snacks, you're welcome to.
Snacks.
So much either. On 21st? Yeah.
Here's candy and something. Cool. I was excited for Japan to return.
It's such a weird weather system this year.
Yeah. I think it's gonna be quite dry.
I agree.
Sun. That is sun.
And reading that's an X-ray. Why like that?
Why something like that?
Why colors like that?
Oh, I mean, anytime you have something in like X-ray, you could present it in black and white, that's what your eyes would see. But of course, it's easier for our brains to conceptualize if you take a multi-channel instrument and then you map them, right? So generally speaking here, a little hard to see here, but there's like purples and howdy. There's purples and greens and reds in here, and you'll take the energy channels in your instrument, and so purple will still correspond to the most energetic X-rays, as opposed to red, which will correspond to the least energetic X-rays. Mixing?
Oh, no.
Oh, thank you.
Those from the band.
Okay, all right.
Something.
All right, ready? Fine. We're not gonna do rocks, but we'll do rock things. We're gonna do sun. We're gonna talk really quickly just about things about the sun. We'll talk about what nucleosynthesis is for like, for like 10 seconds. We'll talk about black body radiation. This is where we're gonna spend most of the next couple of days of class. It's talking about how do we characterize the temperatures, right, of objects. How do we think about the energy from the sun and how that goes into the dynamics and the energy of the systems that we're thinking about. So we'll start just by thinking about it generally, and then at some point we'll start to apply it. We'll apply it both in atmospheres as the driving force of atmospheres, but also we'll think about it in the context of dynamics. Because if you take a rock, you shine a light on it for billions of years, that gives it enough energy to change its orbit. We'll prove it. Okay. This is the sun. This is not the sun that you would see with your eyeball unless you could see the X-ray. And I don't think anyone has X-ray eyeballs. Does anyone know what an X-ray telescope looks like?
The result.
No. Like how you build one.
X-ray telescopes are really strange, right? You think about it, X-rays go through most things. So with a normal telescope, you have something like this. You have two lenses. You have this canonical picture, right, of like light, visible light going through like this. An X-ray telescope basically has something like this. And at the very end, you have this large area here to collect X-rays on the off chance that you happen to.
So it's like a guessing,
What?
like a guess shot?
No. So like, you don't have these lenses that are trying to grab them. You're trying to like maximize surface area.
So every surface is just like collecting those X-rays.
Well, you need to still be able to tell where it came from, right? So we can get into that. I'll show you an actual picture of it, but they're not designed at all like optical telescopes. You know, right? If you think about a radio telescope, what's that? Yeah, it's like this. And it's the same design, right? Collecting area, bounces it all to here, and then they collect it here. But you have to have the appropriate size objects in order to determine where to be. So for example, X-ray really loves pulling electrons off of materials. So you can imagine that if you just took a piece of glass, it would just strip the electrons off the glass. That's all it would do. Okay. Anyway, you can build them. They're cool. I guess if you took Astro 4000, I don't know what they're. You won't see this with your eye. Different colors here come from just moving the X-ray region. You know, when I say X-ray, of course, that's a whole spectrum of X-rays. There we go. Okay. There's the sun. It's big. Bigger than Earth. It's hot. Luminosity is what type of unit? Energy per second, which is a. Nope, energy is a joule. Watts. Yes, and it's what type of unit? Power. Ultimate power. Okay. All right. Radius, big. Rotation. Yeah, quick. How fast does the sun rotate, by the way? How fast does Jupiter rotate? 10 hours. Good. Wow. Slow. Idiot, man. Is it surprising? I mean, that's almost a month. Coincidence? I think not. No, it is. Okay, surface temperature. Up. Go up. Surface pressure. That's kind of a weird thing to think about. Okay, good. So, yeah, there's two things to think about here. When you think about pressure, right? You want to think about the fact that PV equals nRT. So another way of saying that, of course, is that P is equal to rho T, proportional to rho T. So the pressure's really low, but it's really hot. So how do I understand that?
Yeah. inversely proportional.
Pressure really low, temperature is really high. P equals rho T. This is the ideal gas law. P, right? The pressure is really low. The temperature is really high.
Yeah.
The density needs to be extremely low. That's the only way the pressure can be held. Right? And of course, this gets into the idea of what is the surface of the sun. So there's a surface. And at the surface of the sun, okay, this is where photons can escape. That's called the photosphere. That's the first place that photons are not bumping into other photons or other atoms, specifically hydrogen and helium. Mostly hydrogen, bumping, and then they can escape. And as soon as they can escape, there is like very little actual protons out here, hydrogen. And that's why when we go back to this picture here, this is the picture of the photosphere. That is the surface of the sun, whereas as opposed to this, which is showing you all of this material in the corona. And this is very hot, very tenuous gas, not a lot of gas particles. But they're very hot. So when they produce light, it's an answer. Central temperature high. That's necessary. Doesn't get that hot, you don't get fusion. Pressure must be high. We got fusion. Good. Composition, hydrogen unit. Okay. Oxygen, carbon, neon, nitrogen, and everything else. That. H. Sun hot, sun hot. Okay. There's a sunspot there. That's one of those locations that the magnetic field of the sun is poking out through. And because the magnetic field is coming out that location, it is colder. And so it appears darker. So the major difference there is that instead of it being 5,800 Kelvin, it's probably like 5,700 Kelvin. Okay. That up there is the Mercury transit, so that's when the Mercury goes in front of the planet. And if it looks like this is fuzzy, right? Guess what it is. So the surface of the sun is convective. If I were to zoom in here, it would look like a bowl of meso soup convection cell. All right. You'll learn about this in 3100, or sorry, 3310. If you take that with Dr. Wimberly. You may learn about this in Astro 4000 if you get to do that. Right now, we're only going to talk about the composition as it relates to where you get all of the rocks that you've ever seen. We'll talk about the surface temperature as it relates to the ability for it to shine, right? We'll talk about luminosity. How do we heat up planets? How do we make the planet worth living on? And I guess that's about three. So that's a flare, and you can see all of that material is moving along the magnetic field lines. So you might think that because the sun is hot, ionized, it must be well mixed. It's not. The sun is doing the same thing that every atmosphere is going to do, and it is in a state hydrostatic equilibrium. What does that word in that order mean? Archer makes it round. We certainly say that in the context of the interior planets, but when I say that about a gas, what was that? You think of water, good, yeah, I would say fluid instead, so that would be more general. Yeah. So what is hydrostatic equilibrium? Let's take the word equilibrium, that means stable, balance of forces. Okay. So what is the balance of forces that we should think about in the context of a star? Okay. Fusion is getting a little ahead of ourselves. We don't know any nucleosynthesis. Not going to teach it to you. Just think about the exterior of the star. Let's take this little piece right here. Everyone said gravity. I like that. Instruction. But which direction does the gravity? That's G, right? Force. And then you're saying temperature. What is that?
So down, it's all in one single state. Two.
Okay, so if you have a hot gas and you don't continue to provide heat, you're saying that eventually it just cools down and then it's not so exciting. I agree with that. What is the process of that gas? Like what's physically happening when you heat up the gas to say the walls? It's exciting, right? And it wants to push apart everything else. So there is a pushing component due to the fact that it's hot. The force of the fact that it's a gas. It's pressing out away from where the rest of the gas is. Okay, so we're gonna change these. Okay. We're gonna call this one the pressure. And when it's pulling towards, we're gonna call this rho. Like gravity term. And this is a statement. Hydrostatic torque. The pressure forces, the ones provided by temperature, are balanced with gravity. It must be the same. Okay. So the sun is determined, the sun's size is balance of its weight, the gravity terms, by the internal pressure. Turn off the internal pressure source, sun cools down, sun collapses. The heat that provides the pressure would leak away within a few million years. They found that out. They found that out before that they go outside of space. So you can do the calculation, and you can weigh the sun and say, well, what if the sun was made of coal? What if the sun was made of TNT? And they tried to figure out what the fuck was going on in the sun, because it was clear that rocks were very, very old. And yet the sun appears to go out in a few million years. So there has to be an internal heat source. Right? Okay, you know what that is? Yeah. Is that it? What? Yeah, how do you get it? Yeah. Turn hydrogens into helium. Good. So atomic nuclei fuse, and they produce lighter nuclei. For example, if you take iron, here. So if you just let me just say it this way. You know the BB chain? You know that already? Master 2300. The proton chain. You know how to make it at home? Yeah, you know those steps. If I give you a bunch of flour and some eggs, you make a cake. If I give you 4 protons, can you make a helium? Okay, so let's start with 2 protons. Okay, they're like, and then one of them is going to switch. The colored in one is a neutron. The not colored in one is a proton. This is called deuterium. D H H F. And then deuterium is like, yay, let's hang out. And you get tritium. Very good. And that is that. Bunch of H's. Okay. And now you're fucked. Because that is not helium, and that is going to decay. And in fact, it does it right away. But if you go over here and you do it again, and you have this guy switch into a proton, and you have these guys over here, and you do this, then these two can interact. And you get that. Helium and 2 protons. And helium at home. Easy. So all you need is temperatures of 10 to the 7 and pressures of 10 to 15, and you're good. And it's very simple. You just need a, stellar reactor and people try to do this. They make claims about cold fusion. They are all lies. Not believe the hype. We can do stellar fusion. They have the incredible strides forward, but it is hot fusion. And that's certainly the future of clean energy. Once it becomes sustainable, just take hydrogen, which is very abundant, turn it into helium. And helium is a resource. So we can even get a usable thing from it.
Okay. So yeah, you can do the math here. 1, 2, 3, 4, 5, 6 hydrogens. Now, of course, here, what I want you to note is that these 2 hydrogens come out. So really, you can compare the 4 hydrogens to helium. And the difference in mass there is energy. What famous equation is that? What? E equals mc squared. This is what that means. Delta. Delta. That's some powers. Good. So you can do that. You fuse shit into heavier and heavier nuclei until you get to iron, and then you can't fuse it anymore for reasons that we won't talk about here. And then each time you get free energy, you just convert the difference in mass into photons, and those photons go into whatever gas you're making to heat it up. Okay. So the composition of the sun's interior is 33% hydrogen and 64% helium. And likely, if you think about the composition of the entire star as a whole, you'll recall that it's about 70-30. So they're about switched there. Why is that? Well, it's because helium, even though it's the lightest, compared to what we think about, it's quite heavy. It's 4 times as heavy compared to hydrogen. So it sinks, right? And what happens is that you got something like, man, I really should have had some better pictures ready to go for this one. But once you learn this all, you can kind of develop your top. So you have 4 helium, and then right outside you have what's called the hydrogen burning. And outside of this is just off hydrogen. And that's instructions. And encouragement. In hotter stellar cores, so for example, like nearby friends who are bigger, they can fuse helium into carbon, nitrogen, neon, etc. Elements heavier than iron can only be made in rapid processes, supernova reactions, or in no-base situations. This is S process, slow process, but it's not really that slow. It's just compare the rapid process. Okay. Universe made a long time ago. Basically made entirely hydrogen. Some helium came along for the ride. It did this. This is called Big Bang nucleosynthesis. Nucleo just meaning the interior of everything that we have, the nucleus, and then synthesis is the creation thereof. The nucleosynthesis during the Big Bang era gave us the original abundances of hydrogen and helium. And throughout the course of the universe, you have simply ground down the amount of hydrogen. There is no way to make new hydrogen. You have some amount of the universe to start with. You're just converting between the different types. Okay. Here's your helium nuclei. That's beryllium. So you might make beryllium in the Big Bang, but immediately. And the only time you get the carbon is when you have 3 normal helium, but that did not happen in Big Bang. When you talk about the Schwarzschild process. Questions about this? You experts, anything that you haven't seen so far? Good. You can use carbon to react to form other heavier nuclei. So, for example, the CNO cycle is a combination of carbon, nitrogen, and oxygen, which helps us to burn hydrogen and turn it into helium as a catalyst. So you don't produce any new carbon, nitrogen, or oxygen, but it is a form of burning hydrogen into helium. And it's more efficient to have CNO. The larger the planet, sorry, the larger the star, the more energy you have available to do fusion. And so therefore you can run through your fuel much faster. Elements that make the planets, that make you, were synthesized by nuclear reactions. Of course, stars, so when they say, for example, you are star stuff, that is what they mean. All the hydrogen in you, the star, all the carbon, that's from the dead parts of the star, all the nitrogen, the dead parts of the star, right? And of course, it is not our sun, it is the stuff that made ours. Universe is going to take a long time to run out of hydrogen, but it will. There's a great book called The Death of the Universe. It just talks about how every star will eventually go out. But don't worry. This is what I want to show you. This is the nuclear chemical evolution of the Milky Way. And this is really important because you're going to see, I mean, we saw this already earlier in the semester when we were talking about the distribution of the stuff that makes rocks, right? So here's the interstellar gas. Interstellar gas is the one that has these circles. We measure this just by looking out at space in between stars. And not surprisingly, the sun is made out of the stuff that it came from. Good, right? So here you'll notice that the blue dots lie basically on top of the interstellar gas, right? But they differ from what are called population 1 or population 2 stars. Population 1 stars are the oldest stars. Population 2 stars, or maybe I'm doing this backwards. I'm doing this backwards. Population 1 stars are the most recent ones. Population 2 stars are older, and they lack heavy metals. So you see here, carbon counts as a metal when you talk to an astronomer. Don't ask me why. Just anything heavier than hydrogen is a metal. They're insufferable. So here you see that carbon, the distribution in population 2 stars is much smaller than in our sun, because older stars did not have enough time to make carbon. Remember that carbon can only be made in the fusion burning process. So the longer you wait, the more that you enrich stars and therefore the universe in all of them. Okay. Yeah, that's what yeah, I mostly said that too. It doesn't have a sharp solid surface. Surface of the sun starts at something called the photosphere. And if you've ever felt uncomfortable thinking about something like Big Bang or Big Bang cosmology, that you can get over this type of thought by thinking about how you see the surface of the sun. So we talked about before, and I already raised the drawing, is that there's a photosphere, and that is the location where photons can escape, right? They stop bouncing into stuff. That's the same way that we think about the cosmic microwave background. That is when the universe expanded to large enough that photons can finally get out. And then they hold on
to their black body temperature as the last temperature that held before they bounced into something, right? So once they get out, they just hold on to that forever. Okay. Absorption of light varies in wavelengths. Different parts of the photosphere, different amounts of light can get out. So for example, infrared light might be trapped in different places than the X-ray. And of course, the temperature varies with depth. So depending on whether or not you're looking at the UV, whether you're looking at the visible, whether you're looking at X-ray, you're actually probing different altitudes in the sun's photosphere. This I didn't hit it. Think about this. Okay. It's easier to think about the sun's quote unquote surface as a luminosity dependent value. So luminosity you integrate over all wavelengths because what you care about there is power. You want to know how hot is the thing. And if you recall, oh, I got this ready. This is wavelength. This is blue. This is red. Right? What is the shape for a star? That's it. What? Let's say, you know, ultraviolet, everything in that direction. I'm saying blue wavelength goes this way, that way. Visible's here. This is not a good way of saying this.
Very big waves and it goes to little waves.
Like between, it goes shallow and from the limit until it approaches and it jumps up. Back.
We'll put in any markings. So this is the basic idea of what type of curve. Is that Gaussian? I know I'm not an artist, but no, not a Gaussian. Yeah, black body curve. Okay. Okay. Black body curves are specific. They have requirements. They're not just arbitrary shapes. Black body curves can be defined by an effective temperature. So while you give off light at all wavelengths at a certain amount, just like the sun gives off a little bit of X-ray, a little bit of visible, a little bit of infrared, you can verify them with an effective temperature, which is where the temperature peaks in the black body curve. So ours peaks at 5,800. It's actually 5,888. It's other numbers, but that's fine. And this is the same where the sun would produce that if it were a black body. Now, the definition of a black body is absorbs all energy does no re-emission. That's the absorbing all perfectly. Absorbing all perfectly means it absorbs everything. That's the definition of a black body. So it's kind of weird to think about, because you would never shine a light on the sun. But that's what the sun does, right? Sun emits and absorbs theoretically perfectly, but of course there are lines. So it's not perfect. Okay.
is it right, 2,700? I think you learned about this, 3,400, that's E and M. All right?
Yeah.
And 3,500, I believe, is thermal.
Yeah.
Okay, so you should know black bodies. Maybe, I don't know if you think.
Never gets plus. Over.
I think
Black bodies?
yeah, maybe once,
Barely.
but like for a super class.
Yeah.
What about 35?
Yeah,
Oh,
no.
Even when I took them, maybe also just barely when I talked about it with an attitude.
Modern we didn't go over black ones at all.
How do you not go over black bodies in modern? Strength.
Yeah. 30.
Okay. Um,
And we're really gonna get to weightings, we're not even gonna get to radiation. Like,
well, yeah, you only get that in EM2.
no, that's what I mean, too. We won't even get to radiation.
Oh,
When you get to electrodynamics and waves, and that's it.
could we be learning this earlier? This is not the kind of gatekeeps black body.
Yeah, no, it's not that it gatekeeps black body, so you need it. Okay. History lesson. Okay. You start with an oven. You know oven is? The jerk pan? The jerk pan? I'm not hungry, I just ate, but you know, it's all good. It's always Thanksgiving, right, in your heart. Okay, you start with an oven. And you think about, we talked about energy being quantized. Right? So quantum mechanics says something along the lines of you get these particles and they produce a discrete amount of energy. Right? And you run into a problem almost right away where a simple oven would undergo something called the ultraviolet catastrophe. And ultraviolet catastrophe essentially says that if you start by imagining that light is quantized, which is the first thing they knew in the late 1800s, before quantum mechanics had these rules about how you could create these like there was no quantum mechanics yet, but they knew that light appeared to come in packets. They were like, well, that's really fucking weird, because then if you have something that's hot, you should get like ultraviolet light from it. And it would kill and burn you and everyone would die. They obviously that doesn't happen, right? So they're like, something's wrong with physics. And so we're going to talk about this, which is a natural progression of quantum mechanics, which takes a few simple assumptions and then like you can describe stars. So let me show you how this is going to work. Okay, that's not well described. We can come back to that. Well, maybe I'll put like 4 or 5 slides together on the history of quantum mechanics. But this one in particular, black body radiation is an idealized case. It says, I'm going to absorb everything, right? I'm completely opaque, can't see. You have never seen a black body radiator. Why? Because you haven't seen it. It doesn't reflect light, right? Okay. It must also emit light at the exact same rate it absorbs it. That's really important. Because if the temperature is not changing, then any energy that comes in must go out. So if you have this imaginary sphere in space, and it's not near anything, great, no big deal. Right? But as soon as you shine a light on it, okay, it's going to absorb all that light, and then it has to emit it as black body radiation. That's where the term comes from. It's an idealized example of how emission of radiation should go, absorption of radiation should.
In practice, this is what happens. This is how we write it. Okay? And the flux is the total power, ultimate power, luminosity, emitted in all directions per unit area. So what is the difference between a flux and the luminosity? Per unit area. Okay? So flux is luminosity divided by area. That's it. Okay. Stefan was like, well, the flux of an object is proportional to the temperature. And they were like, oh, that's pretty cool. And he gets this whole low constant named after him. Stefan's right here. And the flux of the object is just 2/4 for any black body radiator. And you just measure that in the lab if you're just 200 years ago. You just take something and heat it up, and you see how much light you get. Get more light from things that are hotter. That's all it is. It's an empirical relationship. They knew this before they understood why. Right? That's why you have fucking constants. This is my favorite part. Early physics, simple. Just like, oh, I can measure that thing. Measure this thing. All right, let's plot them. They just drew a line through and they fit a curve. Then you get that. And you keep measuring it to better and better accuracy, and you get a beautiful constant exactly that turns out to be super important. Right? Okay. Oh fuck. Okay. If the sun were a black body with a radius equal to its photosphere, the temperature is 5770. So that's not so bad. It turns out that luminosity, I put it like this, you need to put the area. You can always write it like this, that the L is equal to the flux times the area, or in this case, the flux of the sun. What's the area of the sun? Yeah, but we don't use numbers and stuff. What is it? These letters. What?
A with the.
No, come on. Give me what is the A of the circle? Pi squared. Good. What's the A of the sun?
4 pi r.
4 pi r squared. Good. 4 pi r dot squared, right? Okay. And yeah, that's gonna be a big ass number, right? Okay. But now look here, we can solve this. Because the flux, of course, is just sigma t to the 4th. Right? And this would be 4 pi sigma r squared t to the 4th. And it turns out that it's correct. Okay. Cool. You can also, rearrange these and you can get an effective temperature for objects. So by figuring out what the amount of light that it gives off and how big it is, you can say how hot its surface must be. And similarly, if you were to think about, okay, this object is so far away from the sun, let's treat it like it's a perfect black body. Let's say that it absorbs this much light. This is the temperature it should be if it were perfect black body. And then you can tell two really important things. If it's hotter than that temperature, what do you know? There's an internal source of heat. If it's colder than that temperature, what does that say? It doesn't have an internal source of heat, and it's getting rid of heat effectively, right? Could be melting. And so, for example, you can have something like an asteroid with material coming off of it, right? That's getting rid of that heat. Okay. That is the black body spectrum. I don't know what the fuck happened there. That says luminosity per unit area, solid angle, and wavelength. Every day. This is our time is designed to hurt you. Okay, so here's your black body curve. That's the dashed line. And of course, these are the features that we actually see.
So for example, this is angstrom, so you need to convert this. That's 450 nanometers, 400 nanometers, etc. Yeah. There's features in here we're not gonna, I don't know. But that's this one. So I'm just basically a black box. For all intents and purposes. Okay, here is the Planck function. You ever seen this before? No?
Yes.
You seen the Planck function? Okay. We're gonna start on this. Oh, I'll pre-record the lectures. And you can watch them at home. And I'll just go on a tirade about everything. So
I was gonna ask if it's like math heavy or not.
for what?
For riddles. Yeah.
Well, so for these, so what I'll do is I'll try to go through the history of ultraviolet catastrophe and how you define the Planck function. Mostly because it's not really so relevant to planetary astronomy, but I do think you need to know it. Knowing how we get to here, right? Like this is something that you'll derive, and I'm probably gonna have homework on it. Understanding why it's an exponential function at the bottom. You know, this is the shape that makes that curve. And if you just look at this piece, you get a different answer, right? Than if you look at the whole thing. But understanding the result is very different than knowing why it makes sense. And I can try to break that down. Yeah, let me try and do that. That'll just be easier, and then you can look at it at your own. And so I guess next week maybe don't come to class. I won't have Katie covered. I'll just pre-record them. And post them, I guess. Today or something, whatever I finish. Does that work for folks? Okay, and of course you can give me feedback on that as we talk about it, because that's going to be more history than problem solving. Just follow along. Grab the book. Book's really good about this too. Look at the black body derivation in there. I think that if you're considering grad school, you should know how to derive the black body curve. Right? That is like the standard. Okay. That's the Planck function, and we're going to talk about this in the context of here the intensity that you get at some temperature, and you know, not surprisingly, there's the T, this T, and the lambda, they go hand in hand. Let's go back here. Yeah, this is fine. When we talk about the Planck function, you want to talk about how it's distributing energy. So we talked a little bit about how you can have some arc length, something like this, right? And this is like some portion of the orbit. And if this is r, and this is the distance or the angle theta, what's that length? This length from here to here. R. No. You can call it a different R. That's not what it is. I have the things that you need to make it. Yes. Is that true? What if theta is 2 pi? Oh shit, that's the circumference of the circle. What if theta is 0? 0, okay. You get it? Okay, so that's the arc length. Now in 2D, you need something called the solid angle. Okay, that's a little squibbity on this side and a little squibbity on that side. And it makes a little square in the sky. So the entire sky is made up of scribbity plus scribbity, right? Because if you think about it in terms of like pixels in a planetarium, right? Those are all pixels in the sky. Now these are infinitesimal pixels, so it's not quite the same analogy, but you can integrate over the entire sky. And we do in fact do that. We'll need to do that when we think about the total flux from a black body. A black body does not have a preferred direction. It's just a circle that makes light, right? So similarly here, this big omega is the solid angle, and by definition, it includes sine theta and the whole thing around. The units of a solid angle, very unfortunately, are called steradian. They are not radians. They are a different unit. They are just an angle squared. Okay, so that will bother you for as long as you're a planetary scientist and longer as a person. For small angles, it's usually quite straightforward. You just take some small patch of the sky and you multiply them. Like you just treat it as a rectangle. And the only thing you really have to care about is like delta phi and delta theta with this. So you'll see that also in ASTR 4000, which you kind of have these things together. Okay. We've done this before. And we need a briefer. Are you good? Everyone's happy? Here. Okay. So no, fuck that. Let's not do this. You want to do this or no? Okay, but here's how you you have to integrate the differential element of theta and phi. You don't have to do that here, but you'll do it for ASTR 4000. So hold on to these slides. And remember how to do things.
Are you teaching ASTR 4000?
I don't know, maybe. Might quit. No. What?
Observatory?
Yes. Yeah, observation. Yeah, so here's your big omega. And here's 0 to 2 pi. So it's d phi. Okay. And then all you need, oh my god, I went too fast. 0 to pi is sine theta, d theta. And of course, this is the integral of cosine theta pi over 2, and that is just pi. So the entire sky is worth 4 pi steradian. And that, unfortunately, is something that you just have to remember. Similarly, the solid angle of a cone, if you want to use this pi over 8 radians, that is this many steradians. No, this 4 pi comes from the surface area. But this is the same way that you would integrate. So remember how you do this. 4 pi or 2 pi over here. So this is a double integral if you want to do the surface area of an object. You get the 4 pi in the same way. But it's d theta. It's dr at that point. Okay. Okay. There's funny dimensions of the Planck function because you have to integrate over wavelengths this way. You have to integrate over solid area. And you have to integrate, solid angle and area in order to produce a luminosity. So here's your integration. Remember that the flux here is going to be equal to how much you're putting off in all directions. That's the integral over solid angle. And you want to integrate it, so I don't care about the x-rays, I don't care about the visible, I just want the total amount of energy. So this is the total amount of energy times all of the directions that I'm putting it out. That gives me the flux. And then I have to integrate over all of the areas. Okay. So it gives you really fun. Yeah, and you can prove that Stephan's law when we started this. You can prove what the Boltzmann constant or the Stephan constant. Remember this was sigma before, but it's all made of like real stuff that comes from quantum mechanics. And what's crazy is that you go and measure it in the lab, you get really good precision, and then someone comes along and says, "Oh, that's actually your constant. That's actually other constants underneath that hidden constant." You just use scrap paper, but I can do this. I have a Planck Questions? Okay. All right, we're chugging. Here's the Planck function. It really doesn't look that great then. Here's the visible. Here's where you're seeing with your eyeballs. And this is your dotted line is slightly cooler than the sun. Doesn't exactly peak. So it's here. And then a 10,000 degree star is hotter. One thing that's really important to see here, when you write it this way, this is the energy per second per cubic centimeter. This is the energy volume rate over solidity. Does that make sense? You can say this again. Okay. There's energy coming out. Like imagine there's a fire, but it's like, right? All this energy is coming out per unit second. And think of it like water, like per cubic centimeter, there's that much amount of energy. And then throw over the sky. Sorry. Does that make sense? Okay. The units suck, but as soon as we get past that, it's okay. Because the thing that I really want to point out here is that with this particular equation, with Planck's law, every single curve does not overlap. Every single curve is distinct and dedicated only by the peak temperature. What that means is a 10,000 degree star produces more light at every wavelength than a 5,000 degree star, and so on and so forth. Something like a 1,000 degree star would not be visible. Notice that's of course a lot. Questions, comments, concerns?
Be able to see that first. Wait. This one that's 1,000 Kelvin.
Yeah. Right. Yeah, I mean, you might see a little bit. I mean, be better at like reflecting light. But like 1,000 degree star, you know, that's like be very bright in infrared. You're gonna be able to tell that it's hot, but you're not gonna be able to like see it shining. You got 1,000 degree iron filter, like not melted yet. It's just like kind of maybe a little bit red. They call it heat. Okay, almost there. Almost there. That's the little I already said that. Okay, we won't use the Planck function a lot. There's an important consequence because of the shape. Oh, I guess I have to change this. So homework 5, that I believe is what's coming up next. You will prove Weave's law. No, I'll assign this for Thursday. Or it'll come out Thursday. Because I think you're still working on homework 4, right? Have you started homework 4? Get cracking. So I'm gonna send you another one, and this one's gonna be about Weave's law. And it turns out these two things, they're constant. That's the max temperature, or so the max wavelength multiplied by the peak temperature. It's just a constant. And that's Weave's law. And that was again an empirical law, something that they found in the laboratory before you could explain it. And it mostly comes from this ability to tell, based on the shape of the spectrum, right? The shape that we can measure, what the temperature of the object is. So let's say you have only an observatory that can see all these different stars, and all you can get is the slope of the visible. Plot the slope of the visible, it's like red or blue, red or blue. That tells you immediately. This is the most straightforward part. Deriving it. At what wavelength do you emit the most radiation? At what wavelength do you, let's go back. Write it down. Write it down. And don't take all those numbers, just take the first two or three. Got it? Okay, what temperature do you emit the most radiation? I'm gonna assume that we're all the same temperature. Meters, Kelvin? Is that the right wavelength? 934 nanometers. What is that? Look at your books. In quarter max. $700. What color are you? Excuse me? You are not orange. You said 900, right? Infrared. We are all, that's so good and so good. Human beings are all the same color. Just thanks. Okay, so we all shine in the infrared. 9.4. Okay. You call that on my phone. All right, gamma ray bursters. Not gonna do that, we don't have time. Hot. About 2 billion degrees. Okay. We're gonna talk about the albedo and emissivity of objects. In particular, we're gonna talk about how to warm and cool surfaces. So here is this idea of ice sublimation. You take light in, you warm stuff up, right? So here's the sublimation temperature for all these ices. So N2, CH4, you know about it? Methane, sparks, CO2, power of capitalism, NH3, ammonia, cleaning detergents, CH3OH. I guess you guys are right. Water. Okay. And of course here, this is how quickly they're gone in minutes versus gone in 10 to 5 years of sublimation, right? So one thing to keep in mind is that water ice sublimates rapidly at temperatures above 150 degrees. Pure carbon dioxide, about 80 degrees. So while you may have something, say like 100 degrees Kelvin, surface of some planet with frozen water ice, you can still have carbon dioxide in a gaseous form, right? So each of these ices form a boundary in the original protoplanetary disk. So if the ice can condense, then it can be added into the mix to create a planet or a moon. If you can condense water ice, then you'll have more of it. The reason why Europa has more water total than Earth, which is obviously much larger, has to do with the fact that water vapor condense into snow. So each one of these temperature transitions exists in our solar system, but they are not fixed in location. They vary because of wavelength dependence of something called the emissivity. We looked at the emissivity already, right? And we saw there's wavelength dependence. So if, for example, you need like breaking up a certain type of ice, that's where it's going to break up, right? It's the relationship between that type of light and how it's going. So we had this beautiful picture that we just let 10 seconds ago, so I don't have to have you recall it. Just add them together. All right. All right. A lot of letters. See if we can work through this together in 2 minutes. Bodies that absorb perfectly are rare. Generally speaking, you don't have perfect black bodies. So what you do is you have something like an emissivity constant. How much are you getting as a function of wavelength? So some stuff is more reflective at certain wavelengths and more absorbent at others, right? So let me give you an example. Okay. This object right here is what? Glass. How absorbent is it at visible wavelengths? Not zero. Come on now. Almost zero. What color is glass, by the way? It's green. Glass is green. Yes, if you look at lots and lots and lots of sheets of glass, you'll see that it's green. If you go and you stand in a hotel elevator and there's a mirror on one side and a mirror on the other, and you look back and forth and you see a million of you in a line, your you starts to go green farther down the line. Because glass is not transparent fully. It lets most of the light through, but it's green. So it absorbs in those other colors and it reflects green, right? That's why we talk about color. This is blue because it absorbs all the other colors except for blue, and reflects blue. Okay. No, not for glass. Let's hold on, calm down. Let's not have too much fun. Okay, so this is transparent in the visible. If I am infrared, what color is it? It's black. It does not transmit any light in the infrared. So this is the idea of emissivity. Emissivity is a wavelength dependent function. Okay, it says I am translucent in some wavelengths, I am opaque in others. What is an example of an object that you know and love that is translucent in one wavelength and opaque in the other? We're not going to talk about this. We'll just leave this. We're going to use it as a thought exercise before we go into math. We're not gonna- A phone? What does that mean?
Unless it came from mine.
How is it translucent in some wavelengths? Which are the wavelengths?
It's like the light.
Yeah, but which one? Which wavelengths? I want you to think, you know how I give you an example. I said glass. Visible light goes through it. Infrared light does not. So now your job is to come up with an object that has one form of light that it goes through it and another form that doesn't.
Visible light won't go through.
Infrared doesn't go through metal. Right? Think about how your stove works. You spit outside your stove and infrared goes through it. There's the obvious ones, there's the fun ones. Think about this one. I'll give you an easy one. Okay? How does your cell phone? Which one? Which? Radio waves. Radio waves don't see the building. The whole building is opaque to visible and translucent to radiant. Isn't that fucked up? Now, there is an opposite glass. There is a material that you have in your house that has exact opposite properties. It is. You almost got me. You almost got me. No. A mirror is a reflection. But this is a material that is you can't see through it. But infrared light. All right, go ahead and think about that. I'm gonna adjust a lot of these slides. I'm gonna prep us for a really great show on Tuesday. So don't plan to come to class.